My name's Katie Atkinson. I'm a Professor of Computer Science at the University of Liverpool, and I conduct research in artificial intelligence and specifically artificial intelligence and law. I'm also a member of the Lord Chief Justice's AI Advisory Group. In this module, I'm going to be giving a broad introduction to the topic of artificial intelligence. There isn't one single universally agreed upon definition of the term artificial intelligence. Broadly, we can think of AI as being about designing and building intelligent machines. But within that, we can also make some distinctions, the distinction between strong AI and weak AI. In strong AI, there are researchers whose goal it is to try and replicate human-level intelligence. And in weak AI, people are more interested in designing and building machines that are very good at solving some specific problem and being able to solve that at least as well as a human can solve it, or perhaps even better. Researchers in computer science have been working on AI for decades, and there are a variety of different techniques that have been developed throughout the long history of AI. First of all, let's start with some of the philosophical foundations. Obviously, when we're talking about intelligence, whether it be human-level intelligence or machine-level intelligence, there are a number of philosophical questions that arise when thinking about how we define that and how we can actually capture that and build it into a machine. Perhaps one of the best-known examples is through the Turing test, named after the famous computer scientist Alan Turing. The Turing test doesn't look at how we specifically define AI, it looks more at how we can tell if a machine is behaving intelligently. The way that the Turing test is set up is if we consider there's a room and that room is divided in half. On one side of the room, there's a human who is sat at a computer with somebody or something on the other side of the screen. There's a dialogue going on between the two parties, and the test is to see whether after a set amount of time, the human can tell whether they're interacting with a machine or not. Computer science researchers have put an awful lot of effort into developing machines that could pass the Turing test, but it doesn't require just one technique. There are many attributes that a machine would have to display in order to be able to successfully pass the Turing test. These cover a whole variety of qualities that we see displayed in humans, things like reasoning, planning, understanding language, and communication. In addition to the philosophical questions about when we can count a machine as being intelligent, there are a whole host of other ethical questions that researchers are grappling with when they're developing AI. These issues cover a range of topics, including whether we should permit a machine to make decisions in safety-critical domains, and we can even take that a step further and talk about if we should actually be requiring machines to make decisions in particular domains when they have been shown to outperform humans. One of the key concepts that embody the notion of autonomy in AI is an intelligent agent and how these can be grouped together into what we call a multi-agent system. An intelligent agent is a software program, and it may manifest in some robotic hardware, but this software program is able to sense its environment and plan and act within that environment in order to achieve some goal. And it may be that these agents can't operate on their own and they require coordination and cooperation with other agents in order to achieve their goals. One of the key early topics that people worked on in AI was problem solving via search. In a medical example, it might be diagnosis of a patient. In a legal example, it might be what should be the outcome of this case. Quite often when solving these problems, there's a space of possible options that have to be searched, and each path has to be searched in order to find a particular goal state. There's the first issue of how do we actually represent the real world in all its messiness so that an intelligent agent can understand what that world looks like. Then there's knowing which actions lead from one particular state to another and how we ultimately get towards that goal state. And we have to be able to write that down in very precise terms and then define algorithms that allow us to search through a space of different options. A good way to think of this is in terms of a route planning example. You can think of going from one city to another. So if you could think of travelling from London to Liverpool, then we know that there are lots of different paths, there are lots of different options, which mode of transport you take, which route you take, and then we have to devise algorithms that search through those options and maximise over some important criteria. So it might be that you don't care so much how long it takes as long as the particular option that you have is an inexpensive one, or it might be that speed and convenience are your primary concerns and you're willing to pay more to compensate for that. So think about how we would represent that problem so that a computer could tackle it and get to the goal state of getting us from some city A to some city B via the most efficient and cost-effective route. So search was one of the early topics that was worked on, and that has been applied to a lot of different problems. But also we need to think about how this can be extended to planning both in the short term and also in the long term. Planning is a very well understood topic in AI, and in order to get from some situation A to some situation B, we have to make a set of plans and be able to execute those with the space of resources that we have. That leads to the question of how do we actually represent this knowledge so that an intelligent agent could have it in its head, so to speak, and how it could reason over that knowledge. There are multiple different ways to represent this knowledge, and a popular one has been using logic. There are all sorts of different logics that can be used to represent complex physical notions in the real world, such as properties of the world, objects that exist within it, and more difficult concepts such as time and obligations and permissions. Once we have a representation of these real-world concepts, then we have to enable the computer systems to be able to reason over those. And again, algorithms have been developed that are able to use this logic to enable agents to reason about what to do and how to go about doing it. When we think about representing this real-world knowledge, another concept that we have to account for is uncertainty. The physical world is inherently uncertain, so it's not always the case that our actions will lead to the desired state. We can't always account for the actions of others, and we live in a world where uncertainty is present, and we have to be able to represent that uncertainty in AI systems. And a way we do this is through the use of probability theory. We can use probabilities to represent the fact that we might think an action is particularly likely to end up in one state, or it might be less likely to end up in one state and end up in another state. And we can also add probabilities to the certainty of information that we hold within our intelligent agents. Another topic within AI that has seen a recent surge of interest is machine learning. With the computational power that we now have, our computers can handle very large data sets and can do reasoning over those, and we've got some very well developed machine learning algorithms that, coupled with this computational power, can be used to draw insights out of this data. There are three general techniques within machine learning. First is what we call supervised learning. In supervised learning, we have a set of labeled data, and we use this set to train a machine to be able to classify data into categories. For example, think about a set of photos of cats and dogs. And the goal that we have is wanting the machine to be able to distinguish between photos of cats and dogs. So what we do is we take a data set and we train the machine using the supervised machine learning algorithms to be able to recognize the distinction between cats and dogs. And once we've given it enough examples to learn what the features of a cat are and how they're distinct from the features of a dog, then we can test that learning by providing new examples, and the machine should be able to correctly classify the photographs into those two different categories. So that's just one simple example, and that can be applied to a whole host of domains. And there has been a lot of work in AI and law that has been using these classification techniques that are very well understood now. A second technique within machine learning is called unsupervised learning. And in unsupervised learning, we don't have those nicely curated labeled data sets. So what we do is we take our data and we feed it into the machine, and we get the machine to perform the learning by identifying distinct clusters. Whilst this can be more of a challenge where we don't have these nicely curated data sets, we still do have well understood algorithms that can perform unsupervised learning. The third area of machine learning that has recently received a lot of attention is reinforcement learning. And what we're doing in reinforcement learning is teaching the machine to learn by giving it rewards and punishments, so to speak. Rewards can be thought of in quantitative terms, where we give higher values for a step that takes us closer to a solution, and we give the machine a lower quantitative reward for a step that takes it further away from the solution. There are theories from psychology that tell us that this is similar to the way humans learn to do some tasks. If you think about a toddler who is learning to navigate their way through the world, they learn by making mistakes and rectifying those mistakes and not making them again in future. And that's how we learn to do everyday tasks like moving from crawling to walking or acquiring language. Reinforcement learning is currently being used in a number of successful applications in general AI. One particular application where this has been used is in Google DeepMind's AlphaGo program, which was the first software program to beat a human world champion at the game of Go. Another area where we've seen great strides in recent times is in natural language processing. We already have success in natural language processing being deployed within the everyday technology that we use. If you think of the smartphones that have intelligent assistants built into them, they're able to a good level of capability understand human natural language and also give appropriate responses. In order to get natural language processing applications up to a human level of intelligence, they'd have to be able to understand difficult concepts such as jokes and rhetorical structures that are used within everyday human language. This is an area that has currently seen a lot of progress in recent years. Moving away from thinking about how a machine understands the world and how a machine can reason about what's going on in the world and solve problems, there's also the issue of navigation of the physical world for robotic agents. There are a lot of robotics applications that are very well embedded in industry today. If you think about car manufacturing plants, they use robots in order to be able to assemble the different parts of a car, and they're easy to program because they're doing the same repetitive task over and over again. The next wave of robotics that researchers are working on is being able to have the robots act in an autonomous manner, not just executing the same repetitive steps over and over again, but being able to move around their environment and being able to do higher cognitive tasks. Robots are being developed for application in a number of different domains. In the medical domain, they've been used by doctors to assist with surgery. They're being developed for use in chemistry labs, and we've also got the more well-known applications such as driverless cars. There are a number of different challenge topics that researchers in AI work on in order to help them advance the field, and a good example of this is in robotics. One of the most famous competitions is the RoboCup competition. The competition, which has been running for quite some years now, was originally set up with the aim of having a team of fully autonomous robots that will be able to beat the human world champions by the year 2050. So whilst there's a lot of fun involved in this competition, the real aim is to drive forward research and development in the field of artificial intelligence. In order to solve this problem, researchers have had to make advancements in a number of different topics. For example, how the robots sense the world, how they use that information to think about the next steps and how to coordinate with their teammates, how to move the ball about, and importantly, how to score a goal. We see developments from competitions such as RoboCup driving forward advancements in other application areas as well, because quite a lot of the time the algorithms are not specific to the particular challenge area and can be easily applied to other domains. A lot of the developments within the field of artificial intelligence have been driven by academic research, but we're now seeing a lot more effort being invested by industry into tackling and solving AI problems and getting these deployed in the real world. The obvious examples are the big tech companies that have large research and development departments. And we're also starting to see a lot more collaborations between the different stakeholders, the academics, the industrial partners, and the people working in specific professions who are wanting to make use of AI technologies to help drive forward innovations in their area. We're now starting to see a lot of these collaborations bear fruit, and that's because of the computational power that we have today, the well-understood AI techniques that have been developed over many decades, and also the desire from different professions to start deploying these technologies in practice. Whilst we're nowhere near developing machines that can display human-level intelligence, AI applications are being developed and deployed that are proving to be of use in solving problems for a number of different stakeholders. AI is now routinely being deployed in the world around us, in the supercomputers that we hold in our pockets that we refer to as smartphones, and through various bits of technology that we interact with on a daily basis. Many important philosophical questions still remain about the deployment of these technologies in terms of the ethics and where we want and don't want to be delegating decisions to machines, and regulators and standards committees are engaging with AI researchers on these topics. As we start to see the increasing deployment of AI in a number of different professions, including law, we need to ensure that all relevant stakeholders are brought together so that AI can be developed in a responsible and ethical manner such that it benefits all in society.